Hi, in this lecture we are going to go over the standard normal distribution. So we have already seen normal distribution is something like symmetrical curve with some mu value, and you can interpret the x scores also in terms of one standard deviation, positive, negative one standard deviation, two positive, two negative, and so on. And that's in terms of x. So sometimes it's better to, sometimes it can be the area of interest can be calculated in terms of simply one standard deviation, two standard deviation, and three standard deviation. At that time, we make use of that 68, 95, 99.7% rule, representing 68% as one standard deviation, area within plus minus one standard deviation, that's around mean. Two standard deviation is 95%, and three standard deviation plus minus, that's around mean again, 99.7%. But sometimes we are interested in calculating area. Let's say if your mean is 40 and let's say your standard deviation is 10. Sometimes we are just interested in calculating, maybe let's say finding an area less than 47 score. So if x is less than, or if the student score on midterm is less than 47, what is the proportion of that student? So in that case, it's difficult to simply make use of this formula or rule, because it cannot be interpreted in exact whole number of the standard deviation. So at that time, it's very useful to transform this x distribution into something called as z distribution. And z distribution is also a normal distribution. You can see that this is x normal distributed in mu and sigma. Z is also normal distributed, but with mean being 0, and then you're going to have standard deviation as some 1 z-score, negative 1 z-score, 2, 3, negative 2, negative 3, so on. So simply speaking, it's like some scaling. So you're scaling it for proper graphical presentation. Just like that, you can think of you're scaling it for making use of some statistical techniques, such as in this case we are going to make use of table B in hand calculation, but you can also use software. But in either of these cases, you need to know the z or score, that is the standardized version of your x variable or the variable that you're studying. As in this case, that's going to be score of students on midterm. So that's how you do the standardization, and that's why you do standardization and get the z-scores. So you can simply see that if you have this height data example, mean 64.5, 2.5 standard deviation, you're transforming it to z distribution now from x, with mean now for changing from 64.5 to 0 and the corresponding z value. So if you standardize this z-score, z-score measures the number of standard deviations that a data value x is away from mean mu. So how can that be interpreted? So to calculate that, we have this formula z x minus mu upon sigma, because we are looking for some particular x value which will be away from mean either side. So that's why we are subtracting it. And then we also make use of distribution, or the distribution of data around mean in terms of standard deviation. That's why we are dividing it by standard deviation. So now let's think, if x is one standard deviation larger than the mean, what is going to be z? So in other words, we are saying if x is one standard deviation larger, that's why addition, than the mean, So if this is the x, what is going to be z? So you simply substitute that value in here. That's nothing but this minus mu upon sigma, and you're going to get the z value as 1 if x is one standard deviation larger than the mean. So that's one concept. Similarly, you can think that if x is 2 standard deviation larger than the mean, so 2 standard deviation x, 2 standard deviation larger than mean, substitute that value in this formula again, and then you're going to get the z-score as 2. So z-score 2 is nothing but 2 standard deviation larger than the mean. Z-score 1 is nothing but 1 standard deviation larger than the mean. And you can also notice that if x is larger than mean, z is going to be positive, and x is smaller than mean, z is negative. Why is that true? Because you might have x data, let's say height of patients or something like that, 60, you might have one standard deviation height as 80 and one standard negative as, this is a negative one standard deviation, this is positive one standard deviation as 40. So you know both these values are positive as well. But whenever you transform that z distribution, x distribution to z distribution, your mean is going to be 0 and your corresponding z-score is always be positive something. So in this case, let's say if this is the one standard deviation, is going to be one positive 1 z-score, and you can also get positive 2, positive 3, everything will be positive on the right side and everything on the left side is going to be negative. So even if x is positive number 40, but since it is smaller than the mean, it's going to be z-score which will be negative. So z-score is going to be negative. So when x is smaller than the mean, z is negative. That is another key piece of information. And this is simple example given to you how to make use of this z table or z formula to get the z, but actually you're not required to transform the data into z because this particular x value, this is the x value, this is normal distribution mu and sigma. You can simply find that by 68, 95, 99.7 rule, but if you want to give it a try as a starter example for how to substitute these values, you can take a look at this. Z is going to be x minus mu upon sigma, and then you plug in all this number, x is this, and you're going to get it as one standard deviation. So whenever you solve these kinds of example, make sure your first step is draw the area or the density curve. What is the area of interest that they are asking? So in this case, they are asking everything shorter than 67. So this is the shaded area in light green. That is the area of our interest. So once you draw it, it will become more meaningful in finding the area that will help you. Second step is write down all the values given to you, and you can interchange the first two steps whichever way you feel comfortable. You know this by looking at this convention. N is normal distribution, 64.5 is mu, sigma is everything after that comma, 2.5, x is 67. But just looking at the given data, you cannot say whether it's shorter than 67, so this graphical presentation helps you as well. And then the third step is calculate the z using this formula. And you have proven that z is one standard deviation. But for particular area, next step is you want to find the area using table B. That's for hand calculation, but if you're using software, the software will help you do that. But before looking at how to make use of table B, I just wanted to highlight this other method that you could do or that you could make use of only in this case particular because you know this particular x is simply in some whole number interpretation of standard deviation. So it's actually 67 is nothing but 64.5 plus 1 standard deviation, that's 2.5. So you know it's the area 1 standard deviation away from mean. So everything you want to find out, you can find it just by making use of this 68, 95, 99.7 rule. And there are several ways that you can do it. You can do it 0.65 plus half of 1 minus 68, uh, 1 minus 0.68, that will give you 0.84. But you can also do it as, okay, this is the symmetrical curve, so that's that particular area, the left side of the mean is going to be 50%, so zero point 0.5 or 0.50, and this is plus 1 standard deviation because it's just plus 2.5 addition to this mean, so that's 1 plus 1 standard deviation. And you know area within 1 standard deviation plus minus is going to 68, so on only one side, so that's the whole area, this area, but you only want this additional area, so that's going to be half of that, so that's 34%, or in other words 0.3. So now you know that this is the 0.34 and this rest of the thing all the way is 0.50. That means total area is addition of this, and that's nothing but 0.84. So 0.50 plus 0.34, that's 0.84, and that's how you get the area. So that's by other method. So we are still left with this fourth step for this method number one, that's making use of table B. So I'm going to go over how to make use of this table B. So table B, let me orient you that table B has got Z value on this first column, and you can think of this as course adjustment for Z, and you can also look at row, that is the first row horizontal, that is something like further fine, or I can say additional fine adjustment of Z. So remember, whenever you make use of this particular number inside, you add these fine values to this Z value irrespective of sign, but you always want to keep the sign, mention the sign in the final step, but whenever you do this addition, just forget about the sign, take the module and add this thing. So let's look at now everything inside this, everything apart from first row and first column, which is Z-score, everything apart from that inside this, these all numbers with decimal point and fourth decimal digit, these are all nothing but area of interest under the curve, area of under the curve, or probability of particular event, or proportion of population. So these are all numbers represent these things, and these are all same thing, right? So question can ask you find area, or find probability, or find probability of randomly chosen student having score less than particular x value, something like that, or proportion of women with height less than particular x value, something like that. Everything is same. So what does this number represent? So 0.062 represents z of 2.50 because it's on the 0th fine adjustment with z of negative 2.5. So 0.0062 is the area under z distribution n01 left of z. So this table, remember that this table is always going to give you area for corresponding z value. If it is, let's say this z is going to always give you area left of any corresponding z value that you are looking for. So make sure you know that it's never going to give you area right to the z. So if you want to find the area right to z, maybe you want to subtract it from total area of 1. But that's something that we are going to look a little bit later in next slide. As of now, make sure you know z is going to give you area left of that particular z-score. So another example, 0.060 0.0060 is the area under this z distribution left of z negative 2.5, and 0.052 is the area under z distribution left of z being negative 2.5. But in previous example, we have found the z-score, right? That's one standard deviation, or z of 1, simply z of 1 value. How do we find the area? By making use of this table. How do we find this area? Making use of this table and the z being 1. So for that, we need to actually look at z table for z-score outside in. So we know we are going to look at z till we hit the z as 1, and then we are going to look at this corresponding area. You know, this particular numbers in this particular square is nothing but area, and you know that it's just a 1. You don't have 1.1 or 1.02, 1.03 or 1.04, right? It's just 1. So that's why you're going to look at first column, which represents 0th second decimal value, or two next two decimal values. So that corresponds to 0.84, and that's how you know that that area is 0.84, or in terms of percentage 84.13 if you're representing the proportion. And then you can say the other area on the right side is woman taller than 67% is 100% minus 84.13, that's 15.87. So there are some tips when you make use of this table. One of the very important tip is make use of the information that these all normally distributed density curves are symmetrical. So make use of rules or theory behind the curve being symmetrical. So if area on this side of z, that is the right side of z positive 2.33, is going to be equal to area on the left side of this z. Remember, the table will always give us area left to z, but we can find that making use of table, and we can say on this side it's going to be the same. So 0.999, 0.0099, and 0.0099. Even if the z's are different, these are symmetrical, they have the same magnitude, but it's just on the other side they have the same area. And you can cross check that by looking at this table and looking for z-score with, in this case, 2.33. So 2.3, so you can look at z 2.3. Let me, so 2.3 is right here, and we want to look at 0.2.33. So even the second decimal should be addition to this number as 0.03. So go all the way, oops, horizontally in that same row, and you can find that that is the corresponding area, 0.0099, and that's how we get this area here, 0.009. Another key piece of information, if you are been asked to find this area shaded by this orange color, so let's say every people scored x being more than this particular number, that's what you want to find. Then if you try to find the z-score corresponding by making use of that z formula, x minus mu upon sigma. And looking at the table will always give you area left to the that z, not right. But look carefully that in this particular question, type of question, they might ask you, this is the area of your interest. So what you are going to do, you find this area left of z, that's you're going to get by table B, that orange area, and you subtract it from 1 because you know that total area or total probability or total area under this curve is going to be 1. So find this area, subtract it from 1, and then that is what is the area of this rest of the portion of normal distribution. So these are the two important piece of information from this normal distribution. Third information is like if you want to find middle area, I mean it's not exactly middle, but it's like middle area between two different z points or even x farm points. You're just going to basically transform those x values x1 x2 to, let's say, let me just say x1 x2 to z1 z2, and then you just find the area for z1 and area for z2, and then subtract the area left of z1, that will be larger z, that is positive 2.2. Find that area, let's say if this is the number, subtract that from the other area, that will be for this z2. So if you find this area, subtract this area, you will be getting this highlighted darker yellow color area, right? Key thing to notice, do not subtract just the z values. Subtract the area you found by the z values making use of that particular table, z table, right? Do not subtract z value. That's not going to give you the area. Area subtraction will give you the corresponding area. And you always know that area under the curve for single point, there is no area actually. So just one point, there is not going to be area. So that's going to be 0.